Hey guys, welcome to the video tutorial for chapter 10.1.1. We're going to be looking at field strength today. Now, it looks like we've got a lot of learning objectives today, but quite a few of these are revision material. So I feel it's not too bad. And really, learning objectives 2, 3, and 4 are sort of one big combined learning objectives. So I feel we can kind of get through a little bit more today. So let's get right into it. All right, first up is use Newton's law of gravitation and Coulomb's law. So we haven't talked about gravitational forces in terms of universal gravitation just yet, but you're going to see a lot of similarities between Coulomb's law and Newton's law of gravitation. So down here you can see that on both sides we have force on the left-hand side, and this is equal to a constant, so Coulomb's constant and the universal gravitation constant, respectively on each side. And both of them are interacting on a pair of objects. So with Coulomb's law, it's interacting on a pair of charged particles. And in gravity, any object that has mass, there is going to be a gravitational force of attraction between that. Now, what's also similar between the two is that there is an inverse squared to distance relationship. And so you can see that quite clearly down here as well in the two things that I outlined down here. First one is the inverse squared relationship right here. Okay, and then that the product of either two masses or two charges will give the force in terms of proportionality. Okay, these are three different graphs that you want to be familiar with, and I would say more importantly are going to be this one here and this one here. So those are probably the two most common ways you will see the inverse squared relationship in terms of force and distance. There is a log graph, but this isn't very common, and it's generally not expected for you to see that, but it is there for your consideration for the math gurus out there. Okay, so in terms of our learning objectives 3, 4, and 5, again, this is mostly review, especially on the electrostatic stuff, and for the gravitational stuff, I'll be going into that in a little bit more detail. Okay, so first up, these are two diagrams that hopefully you guys are familiar with. Okay, and remember that the arrows are indicating that we are talking about point charges. Okay, so any point charge around a positive dot will be repelled away from it, so that's why the arrows are pointing out. And any positive point charges are pointing towards. It's going to be pulled or attracted to our negative charge. As that's mostly review here, is to be able to draw field lines, okay, and to interpret field lines and also directions and things like that. Now, in terms of gravitational forces, remember that gravity is always an attractive force. Okay, so that makes things quite easy, is that it'll always pull things towards it. And so really both objects are being attracted towards each other, but because of Newton's law of inertia, or the law of inertia, the heavier object moves very little in comparison. And so when we have a small object like a person or even a ship or a truck, right? These are small in comparison to objects the size of a planet or a moon or the sun or even asteroids, okay? So, so that's why our diagram is referencing that a large mass of usually about a planetary scale or larger will attract smaller masses towards it and it'll pull it directly into it. Or sometimes we say it's caught in the gravitational field. Now, on the right-hand side, we're looking at a smaller scale here. If we look at it from the surface of a planet perspective, we treat the lines or the force fields, the gravitational force field lines, as if they were parallel to each other. Okay, so we treat them as if they were pulling straight down towards the Earth. Okay, and so we usually draw them parallel to each other. Okay, it would be pointless to draw this like 0.0001 degrees, like something like that. Okay, so it would be a little bit pointless to do something like that. Okay, so we don't bother doing things like that. We just say they're parallel to each other, and it just simplifies our ability to comprehend and understand things. Okay, next up, another quick little review is equipotential, or the idea of no work being done. So you're going to see here that we've got three equipotential lines at 50 volts, 120, and 210 volts. And I've plotted a few little dots around there. And so for those of you guys who had attended live lesson with me, we did these two activities together. And so I asked students to identify, there's multiple solutions actually. So the first one is to, from which 2 points would a point charge have work done on it? And from which 2 points would a point charge have no work done on it? Okay, so what I would encourage you to do is pause the video right now, take a scrap piece of paper or just do it mentally in your brain and make some predictions for the first one and the second one. Okay, so hopefully you have done that activity either mentally, you've taken a moment to think about that. For the first one, where work is done, so that would be from A to B. Okay, this is work done by by the electrostatic force, so it might be, for a positive point charge, you'll probably be pulling it towards it. So it'll probably be from B to A. Okay, because a positive point charge will be attracted towards it. Likewise, you could also have D to E, would be another possibility. So those are probably the two best answers there. Now in terms of no work being done, as long as it moves along the same equipotential line, then no work is going to be done. So that would mean from either D to B or B to D. Okay, so anywhere along this line here, no work is going to be done. Likewise, the same would be true from E to F and F to E. E to F and F to E. And also from A to C and C to A. A to C, C to A. So any of those are correct, okay? If you identified all of them, great, more power to you, okay? But if you could identify at least one, then that would have been really good already. Okay, so here, whoops, I forgot to erase the answers. Okay, well, I've already spoiled it for you guys. So this activity, unfortunately, was, sorry, I left the answers on here. So this was an activity that we did in class, and it was asking you to predict the field lines from highest density to lowest density. So the answer is B, okay, the lines that are closest together, then C, then A, okay? So again, this was revision from chapter 5, and so that hopefully that's, you can always go back and check that out in the chapter 5 videos. Okay, our last learning objective today is to calculate the field strength or charged particles and masses. And this is going to take a little bit more explanation. So let's start with Coulomb's law here. That's a little bit more common here to you guys. So Coulomb's law. And you can see what I've done here is that we're re-representing Q1 and Q2 as big Q and little q. And I sort of used this notation without really explaining it earlier, is that usually the larger mass, we use a big M, and a smaller mass, we use little m. That's why we used little m when we did our calculation mechanics, because it was small in comparison to the planet. Okay, so we very rarely use big M, but now we're going to start using that. So the same is true, so that was what we talked about here in terms of mass, so that's why we have big M and little m. And so charge, likewise, we have either large charge and small charge, big Q and little q respectively. Okay, so that's why the formula is still the same, it's just taken on a slightly different way of imagining things. Okay, so now we're just sort of simplifying that to this. Okay, so I'm going to move that over. Okay, so we just re-represented our formula, and likewise I'm going to do the same here. So we're going to re-represent that as this. Okay, but of course they're all the same, but it's just for our notation purposes. Okay, excuse me. Next up, we have Newton's second law. So that's nice to see. Newton's second law, something you guys are hopefully very familiar with by now, F equals to ma. And what I've done is I've rearranged our electric field formula so that it looks more similar to Newton's second law. Okay, so that's a nice little connection for you guys, is that Newton's second law, the electric field formula, we're actually talking about the same thing. So when we're talking about the acceleration due to gravity, or little g, 9.8, right, on Earth, that's essentially what we're talking about in terms of, actually, I'm also going to do one more rearrangement. I'm going to put charge, and I'm going to rewrite this as charge and electric field, okay? So what we're thinking about as the electric field is actually the same thing, or the same thing in terms of the similarities as little g. So that's the sort of electric field or the gravitational field value that we're talking about. Okay, so when we what we're going to do now is we're going to smash these two guys together. And so I'm going to be doing this together here with you guys. And so because these two are equal to each other now, we're going to smash the other two parts together. So that equals this. And likewise, this over here, right, it's the same for gravity, is equal to mg. I'm just going to write that out then. Okay. Now, the good thing about this is that we can cancel out the little m's. So that's why we sort of changed up our notation. But they are actually talking about the same thing. They're talking about the smaller masses being affected by the greater of the two masses, okay? So remember that the force of gravity comes from, say, the Earth. So this is here. We usually talk about our mechanics section, about things happening on Earth, okay? So the force due to gravity, this gravitational field, okay, is exerted by the Earth, okay, or by the mass of the Earth, if you want to be very, very specific about that. Likewise, the electric field is coming as a result of the electric field here is coming as a result of the larger point charge, okay, and it's acting on the little charge, okay? So we're trying to figure that out, right? So now we've got a new set of equations, which I'm going to clean this all up now. So we're going to write this up one more time. So now we've got E equals to KQ over R squared. So that describes the electric field by the larger charge, and likewise the gravity can be calculated as follows, okay? So we have one other way to figure things out if we don't have like sort of the other parts of it. So let's look at a few examples here. This one is going to get us to practice this formula here. So it says calculate the gravitational field strength at the Earth's surface, where the Earth has the mass of 6 times 10 to the power of 24 kilograms, an average radius of 6,378 kilometers, okay? And so we're going to be using the universal gravitational value, 6.67 times 10 to the minus 11. Let me just double check that, the universal gravitational value. Okay, I'm going to see if we can get some Wi-Fi on here. Okay, so you can certainly check that up in your data booklet. Universal gravitational constant. Yeah, times 10 to the negative, 6.67 times 10 to the negative. Okay, I was right. And next up, big mass is 6. I'm just going to ignore the 0.0 times 10 to the power of 24. And then we're going to write 6,378 kilometers. So that's 10 to the power of 3, and then we square that whole thing. Okay, and you're going to get a particular value out of that. I don't have my calculator with me, but you should be able to compute that. That's just punching things into a calculator. Actually, no, that should be, well, we know that should be something around 9.8. We know that's what it should be, okay? So hopefully the calculations show that as well. Next up, we're going to look at the electric field formula. So now we're looking at this new version. Okay, and so we're just going to make our substitutions then. Calculate electric field strength at a distance of 2 micrometers from a 1.0 nanocoulomb charge. So Coulomb's constant, 10 to the power of 9, and big Q is this guy. So it's 1 nanocoulomb. Nano is 10 to the power of 6. And then 2 microcoulombs, so micrometers. No, nano is 10 to the power of -9, isn't it? Micro, 10 to the power of -9. And then this is 2 times 10 to the -6. And then we got to square that. Okay, so that makes things pretty simple. We can just cancel the two things. And then so what we're left with is 9 over 2. And then we've got that -6 squared. So times 10 to the -12 then, right? Okay, guys, so you can finish that off if you really want to simplify that. And so I guess that'd be 4.5 if we want to just make a quick estimate. And that's it. So for the students that were with me in class, these were some of the extra notes that we sort of talked about. So what I was really trying to explain here is that if you want to think about the idea of equipotential, okay, so equipotential would be like thinking about when you're walking upstairs, right? So when you're walking upstairs at school, right, you are working against gravity, which is why it's so difficult. And in fact, if you want to think about in terms of equipotential, your equipotential is also changing, right? You're gaining more and more potential. So, so we talk about in terms of potential energy. So you're adding like 10 joules of potential energy, you're adding 20 joules of potential energy, and 30 joules, and so on, okay? And likewise, when you're walking along like the science wing in the 3rd floor, so when you're just taking a stroll on the same floor, on the 3rd floor, then your equipotential isn't changing. And so the work that you're doing in terms of the change of gravitational potential is going to be 0 joules when you're walking flat. And that's why it's a lot easier to walk straight, or that's one way to think about that. This was another idea to think about in terms of our field lines. So when the ring sort of is closer in, then you get a higher density of field lines. Okay, so you could have a maximum of say 3 field lines here. I'm just going to use a different color here. So you have 3 field lines there, and here you have 4 field lines. Okay, so you can see as you move further and further out, right? We can sort of even imagine if we were to move this ring even further out, then it would probably just be the 2 lines right here that probably intersect that. Okay, so and that's why the gravitational or the electrostatic force drops off so quickly, right? So you can see that both in terms of calculation and also in terms of like the theoretical diagram. Okay, guys, that's the end of this video. See you guys next time.